Okay, so typically when we do a normal day's lesson, we might be having some discussions, taking a few notes and whatnot. Like I said, I'll collect these notes. Usually you'll hang on to them until a quiz or a test, but this is kind of a separate activity. I want you to have this. But I want to talk about Pod C real quick. So normally throughout the year, we're going to be observing multiple phenomena, things that occur, and try to figure out why they occur the way they do. We're going to ask a lot of questions. We're going to discuss them in groups. We're going to come together as a class and share our ideas, and a lot of times I'll write those ideas down for notes. But PODC kind of basically stands for the general format for how we do things. And the P at first, so before we even do the phenomenon, I'll explain it to you, what I'm about to do, and you guys will make predictions. You guys will predict. Okay, so that's step one. And you'll write down your prediction when we get to, we're going to do some demos today, you'll see. You'll write down predictions on a couple of them. And then you want to write down any observations you can make, as many as you can make. Because the more observations you have, the better your chance of describing it and ultimately solving any problems that might come about due to this observation. All right, D, there's actually kind of two of these. But we're going to discuss, and we are going to describe. Now, this might be on your own, where you describe it first, come up with your own idea, and we discuss it in groups, and then maybe share out. Or it might be something where you just go to the tables and you discuss it first, and then as a group, you try to describe what's going on. Okay? And then after we share out, normally as a class, right or wrong, through debate, we try to come up with some consensus, some agreement. Uh-oh, this is early in the morning. I'm usually good at spelling. I think that's right. Consensus, an agreement for the class. So on a lot of these demos I'm about to do here, we're going to predict, we're going to make the observations. Maybe you'll come up with your own descriptions. We'll talk in groups. Maybe we can figure out ways to test them. If you remember the observation game that we did the other day, where you guys were suggesting answers and we were trying to test them. But that's what we're going to do. So we're going to go through these demos. And demo number one, I'll just call it the water jug. Hey, what's up? So the first demonstration is going to be the water jug demonstration, and we're going to talk about measuring amounts of things a little bit here. So here I have, this is just some water with some green food coloring in it, and I'll probably maybe have a volunteer or somebody to videotape the demonstration. But if I look at this, if I measure it, I want to make sure it's flat. What are some ways that we can measure the amount of a liquid maybe? Anybody know? With a graduated cylinder, what does a graduated cylinder measure? Do you know? Like units, measures liquid, measures how much liquid. Anybody know what that measurement would be called? Milliliters. And milliliters are units for measuring in like time, distance, volume. Yes, okay, so what is volume? Anybody know that? The amount of space an object takes up. So that's helpful to use with liquids as opposed to maybe some other types of measurements. Even volume, we can measure volume in different ways. We could take an object, we can measure 3 different sides of it, and then multiply the 3 sides. We can find volume that way, but a lot of times with like liquids, especially when they're in a beaker like this, you can't just really measure 3 sides. You could use formulas for cylinders and find it, but there's little markings on here. You mentioned graduated cylinder. That's very good because graduated cylinders have a lot more marks than this does, this beaker. but this beaker will do for today. But so there's 125, about 125 milliliters. Again, I would want to make sure it's flat. And if there's a little layer or a little dip, if you ever see that, that's called a meniscus. You get that more so in a graduated cylinder where the sides of the container are closer together. But if I look at this flat going straight across, it's slightly below 125. I should fix that. You guys trust me there's 125 milliliters in there? I think I heard yes, maybe no. But anyway, volume of a liquid. If I change the container that I put this liquid into, would you expect the volume to change? How many people, show of hands, would expect the volume of the liquid to change if I put it into a different container? Nobody, good. It's a liquid. Would you expect the shape of it to change? Yes, okay. So liquids, their shape can change, but their volume is going to stay consistent regardless of the container. With solids, when we talk about solids, their mass stays the same all the time. What is mass, by the way? Something to do with space again? Oh, yes. Yep, much better. All right, so we already said that volume is the amount of space something takes up and mass, I believe I heard amount of matter or amount of stuff that's in it. So with a solid, if I change the container for a solid, its volume won't change either. Its mass won't change. Its shape, even that won't change if it's a solid. Okay, if I take this microphone and drop it into a cardboard box and close it up, the microphone is still going to be the same shape. It's not going to take the shape of the box. But liquids are different. So I'm going to pause here for a minute. Maybe get somebody to videotape this so we can see how it works out, and I can post that later. So I just did the demo. Before we did the demo, I put down the P for predict. So we made some predictions about what would happen to the volume of the liquid when it changed containers. And then I did the demo, and you guys made some observations. We have discuss and describe, as well as consensus down there for later, if we get to it. Demonstration number 2. We'll call this cup of water. And we'll kind of talk about our prediction with this as well, once I explain what we're doing. And then we'll make some observations. So I'll kind of help you with those a little bit. So we made a prediction. Some people thought the card would fall off, little water would come out, but the card stayed on. But what was really weird was when I pulled the card away, the water didn't come out like it was supposed to, not until the second try. So again, we can put the D and the C on there for later. And then we will move on to our third and final demonstration. On this last demonstration, there's not going to really be a prediction. So on this one, we can just cross out the prediction. You're going to make observations, though. And so we will get to this one. So nothing unusual about burning a candle. We just talked about combustion reaction. Combustion reaction requires oxygen, which is actually not O. It's actually O2. It's two oxygen atoms stuck together. And then I got rid of the oxygen temporarily to make the flame go out. All that was pretty standard. What wasn't standard was the fact that I ate it. All right. And then we have the describe and discuss. So what I'd like you to do at this point is I would like you on your own to go back. You're not going to discuss. You're just doing it on your own unless you want to discuss it with yourself. But you're going to try to describe what you think the deal was on those observations. Okay? You try to solve the problems that developed because of these observations. Describe what you think is going on. All right? And we have about 10 minutes left. So if you could, we're not going to do the share out and consensus. So if you can just do the describe part on your own, make sure your name is on it, and when you're done, go ahead and put it in the tray.